Hello everyone, my name is Bat-Erdene. I'm a postdoctoral associate in Dr. Eric Finger's lab at the University of Minnesota. Today I will be talking about vitrification and rewarming of magnetic nanoparticle-loaded rat hearts. Before I jump into the experimental section, I would like to briefly introduce this slide. According to the graph, you can see the number of people who's on the waiting list for transplantation is dramatically increasing and totaling over 112,000 people as of March 2020, and the supply of that organ is not enough. As you can see, the gap between the supply and demand is likely wide in coming years. Every organ has different preservation time limits. For example, hearts needs to be transplanted within 4 to 6 hours. But almost 70% of US donor hearts go untransplanted, largely due to preservation limits on assessment and matching. This increases the waiting time until patients receive the appropriate donor organ. Unfortunately, 17% of all patients listed for heart transplantation die before a suitable donor heart becomes available in the United States. Here I would like to briefly mention the various approaches for extending organ preservation. Normothermic ex vivo machine perfusion and subnormothermic ex vivo machine perfusion can extend the ischemic time of the organ hours to days. The current cold standard method for preserving organ is static cold storage, and the hypothermic machine perfusion help to extend that time. If we go below zero, there are multiple approaches for preserving the organ. Supercooling and partial freezing can allow to extend the time for hours to days. And vitrification, which is our study is focusing on to preserve that organ for longer period of times. Here you can see our experimental flow. We used the rat heart as a donor organ. First, we can harvest the heart and cannulate it through the aorta. Then we load the CPA VS55 and silica-coated iron oxide nanoparticle through the heart by machine perfusion. Then we place the thermocouple probes inside the heart and outside the heart. After that, we placed the organ in a cryo bag surrounded by nanoparticle solutions for vitrification, followed by stored in minus 150 degrees Celsius freezer. Then we perform the nanowarming, which allows a radiofrequency coil to rewarm organ quickly and uniformly to avoid ice convective failures. After that, we unload the CPA and silica-coated iron oxide nanoparticle from the heart by using a hypothermic machine perfusion. And finally, we performed an assessment on the heart. In this study, we used standard Langendorf method to cannulate and perfuse VS55 silica-coated iron oxide nanoparticle through the rat heart, which is shown on the photo diagram type A. However, it has some limitations, such as pressure built up in the ventricle as a result of poor perfusion, loading, and washout. Therefore, we introduced the type B cannulation method, which places an additional cannula in the left ventricle. In order to reduce an osmotic shock, we load VS55 as a stepwise fashion with a continuous pressure monitoring and a constant flow rate. When the perfusate reached 100% of VS55, a new stream of VS55 loaded with iron oxide nanoparticle was perfused into the heart until the nanoparticle saturation reached the effluent. The heart turns uniformly black due to iron accumulation. Visually, the washout efficiency of the type B cannulation method was superior than that of type A cannulation. The distension of the left ventricle and left atrium can be observed in the micro-CT image as you see on this slide. To quantify these dimensions, we analyzed the micro-CT images by creating a histogram of 50 axial cross-sections across the type A and B hearts shown on the right side of this column. The left side of this column is micro-CT images of the heart in Hansfield units of 500 to 800, indicating the distribution of the heart. The micro-CT data showed the left ventricle and right ventricle distension in the type A cannulated hearts were superior than that of type B cannulated hearts. It leads non-uniform loading, unloading of CPA and nanoparticles from the heart. This histogram shows higher volume of SIMP in the type A cannulated heart chambers compared to that of type B. Fully distended ventricle causes non-uniform load of CPA and silica-coated nanoparticles as a result of poor washout. For type A cannulated hearts, about 57% of silica-coated iron oxide nanoparticles were loaded in the muscle, whereas the type B, about 87% of SIMPs were loaded in the muscle. This is the micro-CT to define the iron concentration in the heart muscle. In order to do that, we selectively flushed out the silica-coated iron oxide nanoparticles from the heart chambers. The micro-CT image showed the SIMP density in the muscle remained comparable to that of fully SIMP-loaded hearts. Once the heart perfused with SIMPs, fiber optic temperature probes were placed in the left ventricle, right ventricle, and surface of the heart. The micro-CT image confirmed the location of all the fiber optic temperature probes. Then heart was placed in a 2 by 3 inch cryo bag containing 10 milliliters of 3.75 milligram iron milliliter silica-coated iron oxide nanoparticles in VS55. The heart was placed in a control rate freezer by cooling at minus 40 degrees Celsius per minute to minus 150 degrees Celsius. During the cooling, we added 25 minutes of annealing step at 1 degrees Celsius above the VS55 glass transition temperature in order to reduce mechanical stress built up prior entry into the glassy state. The blue region indicates the temperature region for particular danger from ice growth. To support these experimental thermometry observations, we performed finite element modeling to estimate the thermal behavior not only at the sites where the thermocouples were placed, but also throughout the heart. These are the color map representing the temperature distribution of the heart during the cooling. You're looking at the 3 states of cooling: before annealing, after annealing, at minus 122 degrees Celsius, and close to equilibrium around minus 150 degrees Celsius, which is a storage temperature. Here you can see photos of vitrified, cracked, and devitrified hearts in VS55 and vitrified heart in VS55 and silica-coated iron oxide nanoparticles. Cryobags containing vitrified hearts in CPA solutions are clear with heart appearing, and cracked heart and devitrified hearts were easily identifiable. However, successfully vitrified hearts in VS55 SIMP solution was unable to visually examine the state of interior of the bag. Therefore, we have used micro-CT to take a look inside the vitrified sample. The micro-CT images show a uniform signal without visible fractures or ice crystal formation that suggesting the vitrification. After the vitrification, rewarming of the heart was performed. We compared the physical characteristics of convectively warmed and nano-warmed hearts. To assess convective warming, VS55 loaded hearts were placed in the same cryobags and the same volume of surrounding CPA solutions as the nano-warmed hearts, but without silica-coated iron oxide nanoparticles. Then we cooled to vitrified states according to the same cooling protocol. The convective warming was conducted in a 37 degrees water bath, and nano-warming was performed in a 15 kilowatts RF coil, radiofrequency coil at the 185 kHz as shown on this slide. The data shows the nano-warming rates were fast and uniform comparison to that of convective warming. This graph shows the maximum temperature difference between the rewarming in convectively warmed hearts and nano-warmed hearts. The temperature difference which drives thermal stress was larger in convectively rewarmed hearts. After successful rewarming of the hearts, we unload the silica-coated iron oxide nanoparticle and CPA in a stepwise fashion. Convectively rewarmed hearts showed a lower perfusion pressure compared to the pressure of nano-warming during removal steps, which suggested cracking. In order to check cracking, we added the methylene blue dye to the perfusate and clamped the pulmonary artery drainage. Convectively warmed heart was leaking from the side of the ventricle, and the nano-warmed heart was intact, and dye was draining from the left ventricle catheter only. And the visually washout efficiency of the type B cannulated hearts were superior than that of type A, as I previously mentioned on the slide. Here you can see the pre-SIMP loaded hearts, post-SIMP loaded heart, and post-washout. The efficient washout as characterized by ICP-OS and the residual iron imaged by micro-CT and MRI. ICP-OS data showed 93% of loaded SIMP was removed during the unloading. The SIMP loaded and washed out hearts were processed for histology with Prussian blue staining to detect residual iron outside of the vasculature. The image showed that blue staining pointed arrows indicate silica-coated iron oxide nanoparticles in the vasculature. There were no SIMPs in the parenchymal spaces of SIMP loaded and washout hearts. And finally, we performed the optical mapping and histology and confocal imaging on the hearts. Nano-warmed hearts retained some electrical activity during optical mapping. And the CPA, silica-coated iron oxide nanoparticle load unloading leads small histological changes. And the nano-warmed hearts were shown to be largely equivalent in tissue integrity and morphology to the CPA, SIMP loaded and unloaded hearts. In conclusion, this work demonstrates physically successful heart vitrification and nano-warming that biological outcomes can be expected to improve by reducing or eliminating CPA toxicity during loading and unloading. I would like to take this opportunity to express my gratitude to all of our collaborators and the lab members whom contributed to success of this research. Also, I'd like to thank to the NIH and NSF funding to allow us to perform such exciting work. Thank you for your attention.